Okay, I'm Ken Sandage, a Raleigh Professor of Materials Engineering here at Purdue. What I want to tell you about today is a platform technology for fabricating toughened, low-cost ceramic parts for ultra-high temperature applications in friction, stir welding, heat exchangers, and rocket and turbine engine components. So there's an ever-increasing demand for higher efficiency and performance in systems that mandates higher temperature materials. This includes higher temperature turbine engine components for fuel-efficient aircraft, higher temperature heat exchangers and turbines for lower cost electricity production, higher temperature nozzles for rockets for defense and space, and higher temperature tools for friction stir welding of strong welded parts for manufacturing. So what you see here are a number of systems of the type I just mentioned. On the upper left is a concentrated solar power system, basically a field of mirrors that are focusing sunlight to the top of a tower, heats up a fluid at high temperature, and that heat from the fluid is eventually used to spin a turbine to create electricity. On the right is a schematic from General Electric of a combined cycle gas power plant. And both of these systems need higher temperature materials for more efficient electricity production in the heat exchanger, in the turbine, in the case of concentrated solar power, in the receiver. On the lower row, you see an F-22 Raptor, you see a rocket, a solid fuel rocket. In the middle, the USS Independence, a combat ship, and on the right, a Tesla car. So in terms of the aircraft, we need higher temperature components for the turbine. For the rocket, we need higher temperature nozzles. And for all three, we need higher temperature friction stir welding tools to be able to manufacture them better. So the issue is advanced steels, nickel-based superalloys, and other metal alloys are reaching, if they haven't already reached, their high temperature limits. So we need materials that are more mechanically robust than structural metal alloys for use at high temperatures. And the solution, we believe, is the platform technology we've developed for making toughened high temperature ceramics. And so the problem is, as I mentioned, if you plot the maximum stress allowed for metals as a function of temperature for stainless steels, nickel-based superalloys, etc., they all nosedive above about 600 C. And so the mechanical properties are just not good enough. Whereas our material, the produced toughened ceramic composite, is way above that. You can see at 800 C about 57,000 psi. Much stronger, much tougher. So an application of this, as I mentioned, is friction stir welding. So in friction stir welding, you take two pieces of metal, you put them together, and the tool then spins in between them. The idea is to create heat through friction to make it soft, but not to melt it. So here's a movie that's playing, you'll see what I mean. So the tool kind of drills into the two pieces of steel. Once the shoulder hits the steel, it'll get hot, but not hot enough to melt the steel. So friction stir welding is a solid-state, non-melting technique, hot shearing method. Because you don't melt the metal, you don't suffer from the defects that occur upon melting the metal. So defects are avoided, you can make higher strength, thinner welds. So right now, companies like Boeing, Airbus are using it to make aluminum welded parts for aircraft frames. The problem is you need higher temperature tools to be able to friction stir weld steel, superalloys, and titanium. Tools like tungsten and rhenium are high enough in temperature, but they erode. Tools like cubic polycrystalline boron nitride fracture, and they each cost thousands of dollars each. So instead of doing that, so here are the existing materials. Hardened steel works for aluminum, but is not high enough in temperature for the other higher temperature alloys. Tungsten rhenium has a high melting point and is fracture resistant, but it's expensive and it's erosion resistant. Polycrystalline cubic boron nitride is not fracture resistant and is expensive. Our material covers all of these. And in fact, if you look at the conservatively estimated cost of our tooling, instead of thousands of dollars per tool, it's less than 50 bucks, actually. And so the markets we can address directly with friction stir welding include airframes for aircraft, parts for cars, superstructures for ships, and tanks for aerospace. And the new markets that we can access are the friction stir welding of steel for oil and gas pipelines, defense aircraft for titanium structures, high-strength steels for cars and heavy trucks, as well as for trains and a number of other applications.